Hello everyone, in this video I'm going to design a colpitts oscillator out of a common base amplifier. So to start with, we are going to base our design on the previously accomplished common base amplifier. So this is the one. The common base amplifier has an AC ground for the gate, and the input is driven in the source here. The output is extracted from the drain here. So I need to simulate the circuit. So to begin with, I need to check many things. First, of course, you need to check for the cutoff for each of the transistor, whether you check whether they have satisfied the cutoff condition, and you also need to check whether they have satisfied the saturation condition. And this circuit was based on the previously accomplished one, so I presume the biasing condition is quite okay. Now what we are going to do is to double check the AC analysis, make sure we understand the frequency, the maximum possible frequency. So we simulate the circuit and we plot the voltage gain again. So now, quite obviously, you will attain the gain at around 1 megahertz. And if you design the circuits at around the 10 megahertz, it will still work. It will still work, right? As long as there's a gain, then it should still work. Now, what we are going to do now is to design a frequency within the permitted bandwidth. The bandwidth could be anything higher than 3. So it could be from 3 kilohertz to around 32 megahertz. So we can start now. So we don't need AC analysis anymore. And what we are going to do now is to convert this circuit into an oscillator. So first, we are going to delete the input and delete the output. And we don't need the resistor attached to the drain. Instead, we are going to use an inductor. The inductor, to start with, I will use 10 nano. Not quite large, but it should be okay. So we put a capacitor here. So this is the so-called colpitts oscillator. I would make the capacitance, say 1 N, and here is 1 N. So under this condition, I can check what frequency we are going to generate. So 1 divided by 2 divided by pi divided by square root, sorry, 1 divided by 2 divided by pi divided by square root of the inductance times the capacitance. The capacitance here, we find the equivalent of this, so it should be 0.5 nano. Sorry, nano. So I got 70 megahertz. It's obviously too large. You will not get any good oscillation. You will get the oscillation, but the amplitude will be very low. And I can show you. So if you simulate the circuits in time domain, so the start time, the stop time could be 1 millisecond. The starting time to save the data could be 0, and the maximum timestamp is 10 nano. So it should work. So we'll simulate the circuit. And so you can see I managed to attain oscillation. But the amplitude here is from 2.5 to around 3.3. So the amplitude is no more than 1 volt. This is an indication that I'm now nearing the upper corner of the frequency. And let's check the frequency. The frequency here, if you look at the lower, the lower left corner, you will see that the frequency is 62.5 megahertz. I mean, this corner, yeah, I'm going to show you again, is 66 megahertz. So this frequency is obviously too large. So what we can do is we can scale it down by increasing the inductance and see what we are going to get. So obviously the output amplitude is much higher. It's now starting from around 1 volt to 9 volts. So the amplitude here is around 1 volt to 9.9 volts. So the amplitude is about 9 volts. So it's not too bad. We get almost very good oscillation. And let's check the frequency where we get this. It's 18 megahertz. It's still good. 18 megahertz. 18 megahertz is somewhere close to the upper corner frequency, but it is not towards the stop band. So I consider this circuit is quite okay. It managed to deliver a oscillated signal with highly amplified amplitude. Of course, you can make it even more. Yeah, let's see if you can make it 50. Perhaps it will be better. So indeed, it is better. Now I'm telling you, if you have an inductor here, then it's not. You will most likely get rail to rail oscillation. It shouldn't be difficult. Okay. Now, uh, I think it's done.